Hello, we are Team 2. In this presentation, we will introduce our compiler and runtime implementation for ser502 Spring 2018. My name is Zeyong Cai. Next, I will introduce our grammar design and compiler architecture. Okay, let's take a look at our grammar design. The paradigm we use is imperative language, and the name of grammar is called Godfather. We support two types of primitives, the integer and boolean value, and the flow control we support are if else and while. The assignment can be achieved with the operator assign operator. The arithmetic operators we support are plus, minus, multiply, divide, and mod. And we also support different kinds of relational operators like greater than, less than, and so on. The precedence of an arithmetic expression can be override by the parentheses. Because we do not support function, we have a special statement called print to print an arithmetic expression. And another constraint of our grammar is that we require that all declarations can only be placed at the top of a program. Okay, next take a look at our compiler architecture. The front end of the compiler are lexer and parser. Lexer loads the source code from a file and generate a list of tokens. Then the parser will parse the tokens and generate the parse tree. The parse tree can be imprinted by the intermediate code generator. Then we will have the final intermediate code. Next, Hui-Chan will introduce how we use the enter to generate the lexer and the parser.
I'm Hui-Chuan Wu, and now I will introduce at the front end of our compiler. It's basically how does enter generate the parser, the lexer, and the listener. The front end of our compiler is composed of two parts, lexer and parser. Lexer is used to separate a stream of characters into different words, which is a token list. And parser will generate a parse tree with a token list from the lexer. And in our project, we use enter to help us to generate lexer and the parser. And in the diagram below, I can introduce you how we create the parse tree with the string. First, there is a character string chars sp equals 100, and we put this string into the lexer, and lexer will help us to generate the token list. And the token list will be passed to parser, and parser will help us to generate this parse tree. And the enter is very useful. Enter not only can help us to get the parser and the lexer, it also provides us a listener and a visitor, which will be used to traverse the parse tree. And there are a few differences between these two things, and it's introduced on this slide. And this is a grammar file for enter. And Zeyong Cai has introduced this part before. So let's do the next part. I will introduce you the structure file. The file structure in the IDE. As you see, there is the visitor, the parser, the listener, and the lexer. Yeah, and there's also base listener and base visitor, which implement the Godfather visitor. And there is the grammar file. And if this AD has installed the plugin, so we just need to right click it, and if we click this button, generate enter recognizer, we will get the parser and the lexer and those things. Next, I will run the parser tester, and this is the input file. We will generate a parse tree about this diagram or this string. Okay. Okay, you see this is the syntax tree of this program.
Hi, I'm Zutong Wei. I will show you our intermediate code design and show the demo of the generated intermediate code for you. We use 3 address code, which means there is at most 1 operator and 3 operands in 1 instructions. You can see the example below. As you said, this is a very long expression, so it will be spelled into 2 sub-instructions. So in 3 address instructions, an address can be a name, a constant, and a computer-generated temporary. Name and constant is very easy to understand. And a computer-generated temporary is a temporary identifier used to save partition result and will be reused or combined later. So our intermediate code is in the MPI style. The operation is on the left side and operands are on the right side. For example, the branch to label if false rs equals to rt will be translated to bneq rs rt label. For the generator, there is 2 main data structure used, linked list and hash table. First one is used to express the execution order. The second one is used to save the global declared identifiers. The generator procedure can be divided into 2 steps coarsely. The first one is the traverse. Use the enter visitor to access each node on the parse tree and generate the corresponding node and return to the higher level of the parse tree. On the step 2, we get the internal representative of the parse tree statements. Then we need to print it, right? So when we print it, we do it recursively. Means on this example, when we translate the assignment node, we firstly translate the ID and arithmetic nodes inside of the assignment. So after all this procedure, an interval will be generated at the same location with provided Godfather source file. Let me show you the procedure for you. So now we add the root path. We do gradle.bat at build compiler to build our project and generate the compiler, and use java /-jar at build libs gf compiler. Okay, and the file is at data intermediate code test case declaration test. We got the intermediate code. As you see, this is the intermediate code here in the same location as the Godfather source file. So welcome to our runtime expert to tell you how to run this intermediate code.
Hello, Zhang again. This time I will introduce the runtime structure. The execution process of runtime can be divided into 2 phases. The first phase is parsing phase. In this phase, the virtual machine loads the intermediate code from file and generates 2 important data structures. The first one is, of course, the instructions. All instructions are stored in a list. The next is label map. It's used to store the mapping relationship between a label and an index of an instruction. When it comes to execution phase, we have another 2 important core data structures. The first one is the instruction pointer. It's an integer and used to indicate the next instruction we are going to execute. Next is called environment. It stores all the variables at runtime. All variables will be updated and curried from the environment. The running process is very simple. Instructions are executed one by one from the very first instruction to the end. And when the instruction pointer points to the n+1 instruction, the whole program completes. And the instruction pointer can be changed by a jump or branch instruction. Next, I will show the file structure of the runtime. All code of runtime are stored as a runtime folder. It's very simple. We have instruction class, opcode class, and operand class, and of course the virtual machine class. The instruction consists of 1 opcode and no more than 3 operands. The virtual machine also provides some helper methods to inspect the running state of the virtual machine. Now let's show you one example. The virtual machine test is used to test the virtual machine. It consists of many test cases. Let's take a look at one of them. The test case 6 is very simple. It's exchange two integers and print them. This is the source code, and this is the intermediate code generated from the source code. Let's execute it. Now you can see the results are printed here. The following are used to debug. You can see the instructions, the labels, and the symbol table. Next, Bimian will introduce how to compare and run the whole project and demonstrate our program with 5 samples.
I'm Bingbing Yan. I will introduce how to build, compile, and run our project. I will also show 5 samples to show the accuracy of our project. Project is based on the Gradle, so we need to install the Gradle first. After we install the Gradle, we can use the command to build our project. In the command Gradle build compiler to get the compiler. And the Gradle build runtime to get the runtime file. Now we can see 2 JR files are already generated. Then I will use 5 samples to test our language. The first sample is while loop. It is used to test the while loop. This is the source code. Then use terminal to get the intermediate code. Use this command. We can see intermediate code is generated. Now use this command to get the runtime result. This is a while loop result. The second sample is if statement sample. Follows 10 steps. This is the source code. And the intermediate result. Intermediate result. And the runtime result. This is the if statement result. The third sample is compound expression sample. This is the source code. And it gets the intermediate result. This is the intermediate code result. And the runtime result. This is a compound expression result, 40. The next 2 sample is our small algorithm sample. The first one is factorial sample. Follow 10 steps. So there's a factorial intermediate code. So this is factorial runtime result. And as the final sample is Fibonacci sample. This is source code. So this is Fibonacci intermediate code. And this is the Fibonacci runtime result.